solving elements are going to, and some of the non-metal-like elements will go into the silicates. So when they fall into the Earth. And another process I think that occurs at the Earth's surface is the surface atmosphere. So which I'm going to draw you another color, maybe not so beautifully. So in the early atmosphere, to a certain extent, like in this paper they have been talking about, are the evaporation. So because the Earth's surface was liquid and extremely hot, and it vaporized, although it's silicon liquid. But in the later part of Earth, when a lot of part of the metal actually has beginning to reach crystallization, the Earth had a very early atmosphere. So that Earth atmosphere actually also interacted with the magma ocean. So, but in this paper, they mainly talking about this evaporation process without considering the thickness, the atmosphere, etc. So this is what happened on Earth's surface. And at the Earth's interior, of course, not only we have a core forming, but we might also have some later process. Like this paper also mentioned about high diamet, that are some of the sulfides that segregated from Earth's mantle and finally segregated to Earth's core. So this is just some conceptual models that I just draw by my hands. But the consistent evidences mainly comes from the chemistry. That is, people look at the different type of meteorites that are being collected. Some of them are metallic, some of them are chondrite, etc. And some of them contain a lot of volatiles that they contain carbon, hydrogen, sulfur, etc. And also part of the evidence comes from the mantle composition we have right now in the Earth, as well as some other terrestrial planets where people could directly get samples, for example, the moon, or the ones that people get meteorites, like the Mars. And also some other evidence for Earth's core, we don't know. We just know its major elements, possibility of the major elements, but we don't know the details. But what the people do know is that people could do laboratory controlled experiments using this Ford modeling process. Then you know how the elements, isotopes that potentially could fractionate between these different phases. And then at equilibrium conditions or at disequilibrium condition, where people consider about diffusion, then people consider about the time to see how the elements that diffuse into other phase. So, for this paper itself, it doesn't explain everything. So as I sent you two papers, the one paper is about Wang, whose speaker is going to speak. Another one is Li, who wrote an introduction for this paper at Nature Geoscience. As it pointed out that it didn't solve all the problems, but it did help to solve some of the problems, in particularly the sulfur contents and sulfur isotopic composition, in particular, sulfur delta 34. So just for your information, so sulfur has 32, 33, 34, and 36. And so, actually for maybe something that not directly to this paper, but a lot of people, when talking about sulfur isotopes, actually people in particular are interested in, I would say in the recent decade or two, people have measured quite a lot about the sulfur 33 with the idea for the mass independent fractionation. So I won't go into details for that. If you are interested, you could take a look at it. But I would say so. So the key concept for the mass independent fractionation is that these isotopes, they normally fractionate according to how heavy they are. But in some cases, it doesn't. So that process is most likely caused by the photochemical process, which people think that is related to the atmosphere, with or without atmosphere, have the consequences for that. So that's just some very simple introduction that I brought in here. And I'm going to quit from this. And then I'm going to let Wumi to lead the discussion. Okay, Wumi, so please go ahead.
So is my screen visible?
Yes, please go ahead.
Yes, okay. So this paper is this is the paper. So sulfur isotopic signature of Earth that has been established by planetesimal volatile evaporation. So this paper mainly it proposes that this volatile evaporation is the main mechanism by which we can explain the sulfur isotopic signature of the Earth. So Wenjong Wang is the like the first and the corresponding author of this paper, and he'll give a talk tomorrow. So this is his small introduction. So he is mainly an expert in the first principle calculation, and he mainly uses it for to find out the properties of minerals within Earth and beyond. And mainly he explains equilibrium isotope fractionation and partition coefficient, etc., using this ab initio method. And he is currently a postdoc in Carnegie Institute of in Carnegie Institute, and he did his BS from University of Science and Technology, China, and and he did it in geophysics. So this is his basic introduction. So I'll just go into the problem of the paper. So as Dr. Zhang had already explained, the main three theories that already have been proposed. They are, the first one is the planetesimal evaporation, where the like the evaporation of the bit occurs between the melt and the vapor phase. And the second is the core formation, where the metallic core and silicate melt fractionation occurs, and as a result sulfur isotope is fractionated. And the third is the late delivery of the undifferentiated chondrite-like materials. So these are the main three theories that are already proposed, and there are supporting evidences and contradictions to every one of these theories. So in this paper, what they have tried is they have tried to using the first principle calculation, they have tried to constrain the sulfur isotope fractionation between silicate and metallic melts, and then between a vapor phase and a silicate melt. So that would test the above hypothesis, because the core formation, like the process of core formation, have been tested experimentally, but these experiments have mostly been conducted at a low pressure, that is below 2 GPa, and low temperature, that is below 2000 Kelvin. But normally core crystallization condition is at a higher pressure and higher temperature. So and it has also been observed that the structure of silicate melts, it actually varies a lot with the change in pressure. So these experiments that have been done at a lower temperature pressure, it is difficult to extrapolate them and at a higher temperature pressure and believe that the same behavior will continue. Also, this planetesimal evaporation, this method has been underexplored, and so they have tried to discuss these two methods. And also what they have tried to see is if there is no lead delivery of chondrite-like materials, then can we achieve the present sulfur isotopic composition? For example, this is the from different from Earth, Moon, and other bodies. So this is the sulfur isotope composition that has been measured. So these are the measured sulfur isotopic composition, and this is the del S 34 value. So it is basically calculated by this formula, and the reference is the Canyon Diablo triolite. So as we can see that the del 34S value of Earth is it gives a negative value, and it is lower and enriched in the lighter isotope compared to all the other measured values, like for Moon, Mars, and meteorites, and even the ordinary chondrites or the carbonaceous chondrites. They have a value that is higher or heavier as compared to the Earth. So normally the chondrite, the third method, like late delivery of undifferentiated chondrite, that is actually contradicted by this observation, because chondrite value is comparatively higher than the Earth. So however, they have looked further into details. So I'll move on. They have tried to use the first principle calculation, and for that they have basically they made a structure like using the first principle, and tried to calculate the factor f, because just a second. So yeah, this is the equation where you can calculate the value of alpha, that is the fractionation factor between two phases A and B. So this is the formula, and in this formula, this f value is actually this force constant of sulfur. So if we calculate the force constant of sulfur, we can use it in the formula and we can try to measure it. So to calculate the force constant, this calculation of force constant has been done using the first principle calculation. And for that, first what they have done is they have tried to observe that they have mainly taken some compositions, like for example, they have taken a olivine composition where MgO and SiO2 is in a ratio 1:1, and this is the chondritic composition which is normally found. So the melt composition, they have taken two extreme values. One is the oxygen enriched and another is the oxygen depleted. So if we see, yeah, these are the two this is the first composition of the silicate melt, that is Mg32, Si32, O95 and S. So this is the reduced composition where sulfur is in a 2- state, and the second composition of the melt they have taken is this composition where the sulfur is in a +6 state. So using these are the melt compositions that they have considered. Apart from that, they have also taken some other melt composition, which I'll discuss later. So what they have seen is, particularly these two melt compositions, if we see the density, like the radial density distribution and the coordination number of these two melts, they almost show a similar value. For example, here we can see this is the radius of the different like SiO, MgO and MgSi. So if we look at these two diagrams for the S2- state and S6 state, so what we can see is both of them are similar. So based on the composition of the melt, the like melt structure, they do not show any differences. So actually it would have been better if, so they do not show any differences. But if we incorporate sulfur in the structure, and what we can see is that the radius when they are measured, so the radial density function here, what we can see is the radius of SO, that is the sulfur and oxygen radius, is lower than that of SMG and SSI. So this is so at this kind of composition where SO2 based composition, so here the radius S and O bond is this is a possible bond that is formed, and in case of this composition where this silicate melt is present, in that case the radius is lower, or this density function is like this curve is present at a lower radius value for SMG and SSI. So that means that in this kind of melt, the sulfur bonds with oxygen, and in these kinds of melt, the sulfur bonds with magnesium or Si. Also, it is observed that if the pressure is gradually increased, then the coordination number increases, and the structure gradually becomes tighter and more compact. So these are the main two factors, that is the random density function and the radial density function, and the coordination number, or this the bond length or the change in pressure. These are the main factors that controls this force constant. So this force constant has been basically calculated using the first principle calculation, and these are the individual measurements. So these individual measurements have been done, and by this, these are the captured snapshots. So these are the values, individual values, and finally a cumulative average have been taken to reduce the two standard deviation at the end. And we can see that as the pressure increases, the value of this force constant also increases. So from 7 GPa to about 72 GPa, the force constant increases from about 500 to 700. And this similar observation is done in case of every other kind of melt as well. For example, in this melt, with increase of pressure from 6 to 66, the value of force constant increases from 160 to 360. So this exercise have been repeated for the like this is for silicate melt, but the same exercise have been repeated for the iron bearing like the iron bearing melt as well. So for sulfur iron pair, this have been done. And these are the force constants that have been calculated. So after this is for the other two types of melt that is done. So the similar exercise is repeated for every composition, and this is the table that they have used. So these are the cubic cell structures and volume and pressure that they have used for different melt compositions, and these are the force constant values that they have found, and this is the uncertainty they have given. So ultimately, all of this can be explained by this diagram, where it shows that the force constant is composition dependent, and the also pressure dependent. For example, with increase in pressure, the force constant gradually increases. But also for this silicate melt, for these are the two silicate melt compositions, and this is the iron bearing melt composition. So this based on this force constant, they have calculated the sulfur fractionation. So they have calculated the isotopic fractionation. Yes, so this log value of beta fraction, this is the beta calculated. So this beta ultimately controls the composition of the value of alpha. So this is the alpha value. And this alpha value depends on this beta value, and this beta value is calculated in this image. And finally, if we look at this figure, this here we can see that the fractionation factor between different isotopes, between the two isotopes of sulfur is one, it is dependent on composition of the melt. For example, if in case of this melt, where the sulfur is present in a SO2 form, here the fractionation factor is quite high as compared to this, and this is also dependent on temperature, but the variation with temperature is very less as compared to with pressure. So as these are the main points. So the sulfur fractionation factor between mantle and core is determined by the sulfur speciation in the silicate melt, and under the redox condition of co-formation for Earth, Mars, and Moon, this sulfur 2- should be the dominant species in a silicate melt. So therefore, this should be the fractionation factor, and as we can see, this factor is very low. So ultimately, what can be understood is this core fractionation of sulfur, it cannot explain the like the value of sulfur that we actually find in the bulk silicate melt. Also, as there is minimal fractionation between core and the silicate melt, so the composition of core should be also approximately close to the bulk silicate earth. So after they have established that the core fractionation cannot explain the low or the lighter isotopic composition of earth, so they have tried to look into the melt and the vapor phase separation. So here they have used the thermodynamic database, and they have used this grains code to find this out. So from this measure, so here a different species of sulfur they have calculated, and at different temperature they have measured the like the most abundant like the species that would be present in these temperatures, and this is done by minimizing the Gibbs free energy. So from here it is found that almost at this whole range of temperature, H2S is the most stable sulfur like species. So also in this image it can be observed that in this temperature range the H2S is the most common or common species that is expected. Also, if the hydrogen activity or the hydrogen concentration is decreased by 4 orders of magnitude compared to the present solar abundance, in that case, some other sulfur species such as sulfur S2 or SO2. So these are the sulfur species that would be more dominant in case the hydrogen concentration is decreased by 4 orders of magnitude. But however, in our particular, in this case that we are considering, H2S will be the most common phase species. So here, like they have used these force constants. So for the gas species, these are the force constants that they have used, and these force constants have been earlier measured for the silicate melt. So using that, they have calculated the vapor melt isotopic fractionation. And we can see that this is comparatively higher as compared to the core mantle melt separation. So using these values, they have drawn this curve. And also what they have shown is in case of the vapor and melt fractionation, some other factors are important. For example, like how much is the degree of the degree of the vapor saturation. For example, in case 100% vapor, so there is this equation. So 30 in case of vapor melt, this is controlled by two types of fractionation. So one is the equilibrium isotopic fractionation, another is the kinetic isotopic fractionation. So here, if the D value is 1, that is if the saturation is 100%, so in that case the kinetic fractionation does not come into play. So in that case only equilibrium fractionation will take place. But if the saturation is low, in that case anything can happen. For example, it can actually be higher, the value of this del sulfur, so del 34 sulfur, it can actually change from positive to zero, or it can even move to negative. So in this case, the degree of vapor saturation becomes an important factor. And the other thing is the sulfur species in the vapor phase that is found. So as it is mentioned here in the paper, that if atomic sulfur is being released into the vapor phase, in that case, the remaining melt will be heavier in composition. Again, if H2S species is getting released to the vapor phase, then the melt will be lighter in composition. So this species also has an important effect in controlling this fractionation. So based on that, what they have explained is at about if about 90% of sulfur is released, or 90% of loss of sulfur actually occurs during the earth formation, in that case the current the current BSE sulfur isotopic value can be explained. So in this case, so in case of the earth, the bulk the BSE earth, like the bulk earth value of 34 sulfur is lower as compared to the 34 sulfur chondrites. So in this case, the heavier H2S, the H2S species enriched in the heavier sulfur isotope is released. And on the other hand, the composition of moon, the sulfur composition of moon is also heavier as compared to earth. So here they have explained it using the kinetic fractionation, because using equilibrium fractionation, they could not explain it. So they have, what they said is the system was not vapor saturated, and as a result, the kinetic fractionation comes into play. And also at the condition at which the collision of the separation of moon occurred, In that condition, apart from H2S, other sulfur phases like sulfur, sulfur dioxide, they were also released. So in that case, depending on those kinetic fractionation, and they can explain the difference between the sulfur isotopic composition of moon and the earth. So ultimately, these are the points that these are the final points of this total paper. So I'll repeat it. So the bulk earth is actually light sulfur isotope enriched compared to chondrite and moon. And the co-formation, it does not cannot explain the fractionation of sulfur isotope. And if the vapor melt sulfur isotope can actually explain about 0.45 mil at about 1400 Kelvin. So about 90% loss of sulfur can explain the current bulk earth sulfur isotopic composition. And if we need to accommodate the lead veneer process, what they have said is, if a lead veneer process did occur, in that case, the evaporative loss of sulfur would be higher than 90%. And initially, the sulfur value will be actually lower or lighter than it is currently today. Then a lead veneer process would occur and the sulfur isotopic composition would increase further or become a little heavier. And then it would achieve the current abundance of the sulfur isotope. And even the lead veneer could not exceed 30% of the present day budget. And if we assume that the chondrite material had 1 weight % of sulfur, even then, in that case, the lead veneer material should not exceed 0.4% of Earth's mass. And the delta sulfur value of moon earth, they have explained it by the sulfur evaporation under vapor unsaturated conditions of about 94 to 98% during the moon forming event. So these are the main conclusions of the paper.
Okay, thank you, Wumi, for sharing with us about the paper. So now it's time for us to discuss the paper. So do you have any questions? Feel free to open your mic or put in the chat. Actually, I have a quick one that, Wumi, so could you tell us from a more intuitive perspective that when people calculate the force constant, basically between the fractionation of two phases, for example, metal and the silicate, or silicate liquid and vapor. So when people calculate the fractionation, isotope fractionation, then people are basically the force constant difference between these two phases matters, right? Am I right?
Yes, actually the difference matters.
And so normally the higher force constant of one phase, for example, metal and silicate. So if one phase that has a higher force constant, then that means that heavier isotopes that tend to reside in that phase. Is that right?
Yes, that should be the case, because it is also controlled by the bond length. So shorter bond length means a higher value of the force constant. So I guess for shorter bond length, the heavy isotope will be preferred, I guess. Yeah, that is normally how it happens, right?
Okay. The one great thing that for the method that we use is that for first differential calculations, they don't input any empirical equations or empirical parameters. So that's a strong point that they have of this method. So that's what the people would call the ground truth. Because even for thermodynamics, like what we are, some of you might involve with, for thermodynamics, we do have a lot of empirical equations. For example, we assume it is y equals ax squared plus bx plus c. So that is the empirical equation. Then people make the fit. So for first principle calculation, they never have that. So they go all the way to calculate interactions between the nucleus and the electrons, etc. Okay, so yeah, feel free to post your question in the chat or open your mic. Go ahead. Okay, so now you have been speaking, I could insert another one. So Wumi, so to your understanding, do you think that the amount of sulfur matters in the silicon melt if it is a sulfide species?
Actually, it should not matter, right? Because the force constant would not depend on the concentration of sulfur, at least that they haven't considered.
I think they did consider because they tried two different silicon melt composition, do they?
Yeah, but that was based on the oxygen fugacity, like the sulfur 6 minus state or 2 minus state. So two. So
okay, let me see. Okay, that's true though, because okay, that's different amount of oxygen they put in. So that shouldn't matter. But have
I also don't
they looked at the force
think
constant? Have they looked at the force constant difference between? So could you go to the supplementary table where they have the force constant with different compositions, because they do have a composition with the iron, silicon, nickel, sulfur, carbon, and another one with only iron and sulfur, right? That they assume two different types of core.
Yes,
composition.
yes, yeah, that is there. So yeah, that is for the core composition, I guess.
So could we go to one of the supplementary figure where they have shown the force constant?
Yeah. Do I share the screen?
Yeah, please.
Yeah. So this is one for the Fe97S3 melt. And here it is supposed to start average about 140 or 160. So and it will actually depend on the composition. So yeah, but I'm not sure about the amount of sulfur.
So where is the other one with the different core composition?
This is the one.
Yeah, there's another one with the core composition. So this is about 250. What about the other one, Fe3S, Fe97S3? So what is force constant?
So that is about like 160 and 160 and but this is at about 41.81 GPa. So yeah. 41 point, yeah, it is also 240. Not much difference is there actually.
So they do have a little bit difference because okay. So could you go to one table where they do have the force constants of different compositions? I think they have a summary of one table that.
Yes, this is one.
So basically, they want to say the alloy, that the metal and the silicates don't have much fractionation. Okay. Although there is very slight difference in their force constant. Okay, that's also tricks me because basically they are, I mean, do they have the force constant at a zero pressure of this silicon liquid? Because when they compare with the gas species vaporization, then they're comparing with it with the silicon melt at zero pressure, right?
This gas species, I think they have calculated it thermodynamically using this like the other method, like yeah. So this method, yeah.
Okay.
Code.
So basically, I don't know how valid is this Green's code. Okay.
I thought it is written. No, the factors, the vapor. Yeah, this one.
This is the pressures, but it's actually
For vapor, I know that's a common one that people normally use. So when people study for the condensation temperature, normally is calculated at the 10 to the -4 or 10 to the -5 bar. So for this vapor pressure is short, but because they use this to calculate the force constant, then they need to know the force constant of the silicate melt at the same pressure, which
but they have, I think they haven't done at such low pressure, because the pressure are
but they could expect that at a lower pressure, then they're going to have a lower force constant, give the trend that holds. Okay, Umi, let me share my screen. I could share you one thing. So I could share. So I was asking about the composition because I know the composition they put in here. What they put in the core is reasonable, 1.76 weight percent. But what they put in the silicate liquid probably is not that appropriate, unless they think that the majority of the sulfur, or had they later claimed that majority of them that being evaporated. Even by that, I don't think this is right, because, for example, you have 1% of sulfur in the silicate liquid, as what they put in the composition, then you have 90% of those sulfur evaporated, but that's still not right, because our box silicate earth sulfur has about 200 ppm. So 1 weight percent is about 10,000 ppm. So even have 90% of them evaporated, that number still is not right. You still have 1,000 ppm of sulfur left. And so that's why I was asking about this, because I don't think that the silicate melt composition that I put in here is appropriate. And in particular, what is more complex is that there is a sulfur solubility in this silicate melt that varies as a function of temperature and the pressure. So this composition should never be the same. Should not be in the exactly same chemical formula that they write. And it doesn't exist throughout the Earth's mantle. At the shallow part of the Earth's mantle, it has a higher sulfur solubility, and the deeper part it has lower. So I think they put their no matter what their composition are, I think the composition they put have already exceed the sulfur solubility that is possible in Earth's mantle. So I think they have put too much sulfur into their model that doesn't agree with the sulfur solubility, and also doesn't agree with the Earth sulfur composition in the box silicate Earth as what we know today. So actually, that's a little of my doubt that my doubt is that if this change, for example, sulfur is decreased for 1 order's magnitude, and then put in the calculation, I don't know how much impact is that for the first constant. I don't know.
I think,
yeah, go ahead.
I think they'll have to change the size of the unit, like the size of the cell they have considered, they have to change it. Like they have to increase the size and keep the sulfur concentration less. So
yeah, I think that's more problematic, because what they did is that they did a couple of cells, and then for each cell, for example, now they have 1 sulfur. So that I think that's what they probably did. And if sulfur is decreased by 1 order of magnitude, then they won't put 0.1 sulfur in 1 cell, but they have to assume 1 sulfur in 10 cells or something like that. And then they also have to determine how sulfur locates in these 10 different cells, because it's a molecular dynamics modeling that they're going to get. I think that will become extremely complicated. And that normally for first principle calculation, people try to avoid. So that's why when we look at olivine composition, for example, it's very common for first principle calculations where people calculate with mg number of 100. because they want to calculate pure magnesium phosphorite. And then they calculate the Mg number of, for example, 87.5. Why? Because they just want to replace one magnesium to one iron in the cell. So that's the easiest way to do. But if you want to do a magnesium number of 90 of all living, then that makes the model very complicated, because it's very hard to put the atom like that. So actually, that's some of the methods. From that perspective, the composition might matter, but I just don't know how much this will change their results. Probably is the answer that we won't know until people really try it. But my intuition is that the computation amount of computation that is needed will be probably one order or several orders of magnitude more computation resources to complete that process than what they are using in this paper. So that's just my intuition. I don't know. Probably I need to ask the speaker. But maybe Wumi, you may have some more ideas about that.
I think they have to increase the computation part to increase this, to decrease the sulfur concentration. But I guess they'll have the explanation in form of bond length, because what they say that it depends on if sulfur is bonding with oxygen or the metal, that actually controls the partitioning to a certain extent. Yeah. Also, I guess because they have found that there is no considerable fractionation. So even in the composition they have calculated, there is not much fractionation between the core and the melt. So possibly they'll like to more focus on the possible mechanism, that is the vapor and melt.
Okay, I think that's a strong evidence that I could argue that it does matter, because they don't have fractionation anyway. Okay, that makes sense.
Also, I was wondering if similar kind of work has been done on other isotope systems, for example, like nitrogen.
I don't think so. I think nitrogen is much harder to do. Sulfur is more straightforward. This valence state is fixed, and how it bonds with oxygen or how it bonds with iron is more straightforward to do. That's my intuition for it. Actually, I don't know what prevent people from doing that. For example, in this paper, for people measure sulfur isotope, for example, for Jabran Labidi, published in the paper in Nature in 2013, where he analyzed mainly the Morb concentration, the Morb as a sulfur isotopic composition, and compared with meteorites, and then claimed that there's difference between the Earth sample and the meteorite samples. And then at that time, Labranjavadi claimed that this probably occurred at the core mantle fractionation, although he didn't give any reason why that is really the case. And since then, I think people have been thinking about it. But I think one argument that people normally before, let's say in 2014 or something like that, when I had an argument with other people, then some of the people would insist that we don't need to calculate that because it's just impossible, because the core mantle temperature is 4,000 K, for example, and extremely high. And we know that the isotope fractionation is E over RT. So basically the negative RT. That is basically the higher temperature we have, the smaller fractionation there will be between these two phases. But somehow that some people that work on some part of this, and some people that claim, according to my recollection, that under very high temperature, there were fractionation between them. And then people made a little bit of noise. But I think Wenzhong's work, they're trying to pull that back and to say, okay, at a high temperature, probably that doesn't matter. But I think maybe to a certain extent that Wenzhong also want to point out for sulfur oxygen and the sulfur iron bond, doesn't fractionate sulfur isotopes much. I think that's some of the new evidence that Wenjong has been put on in this discussion. Although at that time, I remember when I read this paper, a 2013 Nature paper, in my previous group discussion at University of Minnesota, I was just asking the question that how did the quantum diffractionation possible at a higher temperature? But yeah, at the time, people didn't have any answer in the seminar. People just say, okay, that's just what they proposed, and they didn't do any that's a real thing about it, because they just measured natural samples and saw this difference, and then they claim this the quantum fractionation is the reason for what they saw. So that's it. But it did provide a very good topic that people began to do a lot of more following work. But I think overall now is still not quite straightforward process, because there are many ways that could lead to the same result, and that people are still debating about it. But I think maybe that's a good thing that keep people busy in getting more funding and pushing forward with more experiments and collecting more natural samples to know them. And hopefully for the Mars return mission, we'll get more Martian samples that could reveal a little bit more about that. Similarly for the moon, I think we do need more lunar samples to analyze different types of isotopes. Not only sulfur, but other Chekhov-phi and siderophile elements that will help us provide a better understanding for that, because I don't think that the observation is abundant enough for us to confirm that even our argument to begin with is right, because current argument is mainly based on the meteorites and their measurement. Other than a lot of in situ samples that people collect from other planets. So I don't know. I hope that we're in the coming years that people will have more constraints on this part. And of course, on the other hand, we can have more self-consistent model. Actually, from what we are doing in this group, that we do focus on the machine learning. I think this is I have been talking with some of my other colleagues in the community that is an initiative that we should take. By considering all of these factors together, including all the experience people form together, and provide a self-consistent model. I think that machine learning actually do have a role to play here, although it is not the first principle. So machine learning is not the first principle. This paper that is first principle, and it mainly depends on our ground truth physics. Machine learning is another principle, but it could help us to reveal the truth. I do think that is a direction that worth trying. Okay, I have been talking a little too much. So do you have any other questions or comments, ideas?
I was just wondering one thing, like in case of the core mantle fractionation. So as you said that at a high temperature, there would be no kinetic fractionation. But I guess that is what they have considered, that depending on the composition of the melt, there might be a difference, like the iron melt and the silicate melt. So depending on the the bond length and all, so that kind of fractionation would be there, but that would be very less. And as they have measured that, it is very less. So in similar case, if there is a vapor exsolution or vapor separation, in that case, even if the temperature is very high, but because the two phases are very different from each other, so depending on the type of structures they form, there will be a fractionation of isotope.
Okay. Yeah. So is the phase that a species the locus in that could help to fractionate the isotopic compositions. Yeah, that's why the people working on this different type of phases to try to look for the possible mechanism to explain what we are seeing now.
There is a question.
Yeah. Whether people have that, have hydrogen and nitrogen, I think is very is even harder to get. But they do show some, let's say, there are other metals, I think for metal elements and metal isotopes, people know it much better. That is what is described in the Li Yuan's paper that to introduce this. I encourage everyone to read it carefully so that you will know that people have made a lot of efforts in that direction. However, for hydrogen, nitrogen is more intriguing. So because for volatiles, it's very hard to preserve what they have. Hydrogen, nitrogen, carbon are very hard, and sulfur actually is slightly better because sulfur, to a certain extent, sulfur is better, is easier to preserve and bed them. So it's a total mess. I don't think that we can immediately get the result from that. And for hydrogen isotopes, for example, people have always claimed that the evaporation process is a very effective mechanism to fractionate isotopes. Nitrogen, I think people know less about nitrogen isotopes. And for the elemental concentration, of course, is a mass, but people have been also looking at the elemental ratios. So like my former PhD advisor, Mark Krishman, has been working quite extensively in the recent decade on the hydrogen-carbon ratio, hydrogen-sulfur ratio, hydrogen-nitrogen ratio, etc. So people are trying to look at the elemental ratios to reveal that, not only between the volatiles, but also between volatiles and the metal elements, because that's metal elements are easier to be preserved. So that's how people are trying to do experiments and study the partitioning coefficients, look at the similar partitioning coefficients of the volatile elements and the metal elements. And then you use that metal element, which has been preserved in the natural samples, to indicate the volatiles. So that's about it.
Recently, there was one of our seniors from our department. He came and he gave a talk on the nitrogen isotope. So what he said is maybe you know his name. So what he said is he was working on the experimental fractionation of nitrogen, and even in case of nitrogen for core and mantle separation, there seems to be no difference in the isotopic fractionation.
Sorry, which two?
In the core mantle separation, there is no nitrogen difference in nitrogen isotope composition as well.
Yeah, there's some arguments that people are still fighting with each other. So Yuan Li's group saw opposite things that Celia Dalu saw. So both of them, Yuan Li is someone that we are more familiar with because we traveled to Guangzhou to his lab to perform experiments for Lei and for Ben's projects. And Celia Dalu gave a talk this year in our webinar. So both of them that they saw something that different. They even haven't been able to reconcile with each other, but it looks like both of their experiments at least are self-consistent with themselves. So I don't think that we have a definite clear answer for the nitrogen isotope fractionation. So it is still very vague. People are still doing research on it. Now, I think there are a lot of technical things that will influence the results. Nitrogen isotopes, there are manufacturers who will influence the nitrogen isotopes experiments by themselves, as well as measurements. So it's all very challenging work. So I don't think even people have resolved that through the controlled experiments. But we can see more work will coming out of it.
So I just posted the name of the who gave the talk last.
Yeah, Celia Dalu. Celia Dalu. Yeah, I think I put in the chat. So I think she gave a talk. I forgot which month. You could check our webinar schedule.
Yeah. I attended the talk.
Yeah, and the Yuan Li's paper. So both of them published nitrogen isotopes that have different results with each other, and they don't know why actually. So they communicate with each other. They don't know why. So, but that's fine. Okay, any more?
I have a quick question. The redox state redox state will influence the isotope fractionation of sulfur during the cold mantle and formation. But I think, according to previous research, the redox state of the cold mantle differentiation period is highly debated. So how did also counter this question? to
Okay, I think that, okay, so for the core fraction redox, yes, there are several orders of the magnitude difference that, but I think it's a wide range. People would normally agree. For example, in this case, in the modern Earth, people think is iron will start -2. So let's say something that people would normally agree. But for this question, that for this paper itself, I don't worry too much about it, because for sulfur itself, so the sulfur and the sulfate, actually sulfate. So for sulfur, so for sulfide and sulfate, this occurs at MFQ +2, or is like iron would start +6, something like that. So for sulfide and sulfate transition, they occur at a really oxidized condition. So even more oxidized condition, the Earth's upper mantle. So like only in the arc magmas, for example, they could be more oxidized than that, or some of the crust magmas. So in the Earth's core mantle is very reduced. It's way more reduced that normally sulfur should only exist as a sulfide species, at least as what they claim. I think it's generally right. But in the Earth's core, actually, that's something else that I think that's intriguing to me. Because supposedly at the Earth's core, sulfur, its valence state should be 0. Although, if you write something like this, sulfur 97, 3, then I would consider you have 3 . So I think this is something that I'm not so sure about it. So I think it's worthwhile asking the speaker to ask how he see from his perspective the chemistry, because I think for me that both are ways that could explain. Let's say is charge neutral, but I don't know if the sulfur species, native sulfur species, of course, it will influence the force constant. So I don't know what's the direct answer for that. But I incline to have the second one, because according to the shallow pressure thermodynamic model, it exists as a sulfide, predominantly sulfide species with this composition. But in general, I don't worry too much about it for this. But for some other elements like carbon, nitrogen, there are species transition, oxygen fugacity may be different. So it is case by case. So in this sulfur case, I don't worry too much about it. Okay, I think we have lasted for 1 hour, and thank you very much, Wumi, for leading the discussion. And on Wednesday, we're going to see the speaker, and it's the very last paper discussion we have in the year 2021, and very last talk that we're going to hear in the year 2021. But I think that we are going to see each other in different places. Like this Sunday, we're going to do a hiking along the canal in very beautiful paved way and beautiful fall colors. I hope that we can see a lot of people here in the city, and hopefully in the future, Wumi and Natasha could join us for the hiking too, and Liu Yao too at later part of the year. Okay, good evening, everyone. Bye bye.